Welcome to the deep dive. We got a ton of awesome questions inspired by that mind-blowing mysteries of the atom article, and well, we're going to deep dive into them, unpack the coolest stuff without, getting too lost in the weeds.
Right on. I mean, the number of questions just shows how much we all want to understand these tiny building blocks that make up, well, everything from like why electrons don't just crash into the nucleus to the whole, is the universe just a giant atom thing? It's going to be a wild ride for sure.
Okay, let's just jump right in. The first one that really caught my eye was like, where do electrons even get the energy to keep whizzing around an atom's nucleus? We all kind of picture this mini solar system, but that has some problems, doesn't it?
It does. That simple picture of electrons orbiting the nucleus like planets around a sun, it doesn't really hold up when you look closer. For one, if an electron was zipping around like that, constantly changing direction, it should be radiating energy, like all the time. And if it's losing energy, it quickly spiral right into the nucleus, right? But atoms, well, they're clearly much more stable than that. Plus, atoms don't emit a continuous spectrum of light like that model would suggest.
Yeah.
They emit light at very specific frequencies, more like a barcode than a rainbow. So that whole planetary model, while easy to imagine, it just doesn't match what we actually observe.
So the article you sent mentions Niels Bohr and his revolutionary ideas. What did he do to kind of fix this whole mess?
Bohr, back in 1913, came up with this radical idea. He said, hey, electrons can't just be anywhere around the nucleus. They're restricted to specific orbits at set distances, like quantized orbits. Imagine it like a staircase. Electrons can be on the steps, but not in between. And he said there's a minimum distance, a point closer to the nucleus that an electron simply cannot get to. And this wasn't just guess. It was based on Max Planck's earlier work on the quantization of energy.
Right. Planck's idea that energy isn't a continuous flow, it comes in these discrete packets, little chunks of energy, right? I remember that from the article.
Exactly. Planck had shown that objects absorb or emit radiation in these packets called quanta, and the energy of each quantum is directly tied to the frequency of the radiation. It's all related by a constant, Planck's constant, which is super important in all of this. Bohr took that crazy idea and said, hey, maybe it applies to electrons orbiting the nucleus too. So he postulated that the angular momentum of an electron in an allowed orbit has to be a multiple of Planck's constant divided by 2 pi. Basically, there are only specific allowed zones where an electron can hang out around the nucleus.
So it's not just the distance, but those distances are tied to specific energy levels set by this, like quantum rule. The article also mentions a deeper explanation, something about quantum mechanics and the wave-particle duality of electrons. That sounds pretty intense.
It is, and it gives a much fuller picture of what's happening. Quantum mechanics revealed this crazy idea that everything, including electrons, acts like both a particle and a wave. So instead of a tiny electron zipping around, think of it as a wave that's kind of spread out around the nucleus. And just like a guitar string, which can only vibrate at certain frequencies to make standing waves and musical notes, the electron wave around a nucleus has to fit the space in a stable way. The allowed orbits, as the article probably mentioned, correspond to these stable standing waves patterns of the electron. That first orbit, the closest one, that's basically the fundamental standing wave that can fit around the nucleus without canceling itself out.
Okay, that wave thing is really helpful to visualize. So it's not just specific energy levels, it's the electron itself being a wave that's confined in these stable patterns. The article also mentions a totally different angle, something about energy balance in the atom. How does that fit in?
It's another way to look at it, focusing on the forces at play within the atom. You've got the electron, negatively charged, being pulled towards the positively charged nucleus by the electromagnetic force. But the electron is also moving, so it has kinetic energy, and that tends to keep it moving away. In a stable atom, these two forces are balanced. What's interesting is that the electron's total energy, if you add up its kinetic and potential energy, is actually negative. That negative energy means it's bound to the nucleus. You'd need to add energy to rip it away.
Right, so it's like the electron is trapped by the nucleus. So even without the wave stuff, it can't just crash into the center because of this balance of forces. The article mentions something about quantum mechanics keeping it perpetually stuck in orbit, even in this model. What's that all about?
Even in this energy picture, quantum mechanics is still crucial. It says the electron can't just lose energy gradually, like a ball slowing down. It can only exist at those specific energy levels we talked about, those quantized levels. So, as the electron is pulled toward the nucleus, it hits that lowest energy level, the ground state. And it can't go any lower without breaking the rules of quantum mechanics. It's like there's no basement below the ground floor. To get closer to the nucleus, it would need even less energy, which is simply not allowed.
Wow, that's deep. Okay, let's switch gears for a sec. Another question was about the very beginning, like how did the first atom even form in the early universe? I think the article mentioned some crazy numbers about how many atoms there are out there.
It did. The observable universe, just the part we can see, has something like 10 quadrillion vigintillion atoms. That's a one with 78 zeros after it. And every single one of those tiny atoms, made of even tinier electrons, protons, and neutrons, all came from the Big Bang, the big explosion that started it all. But getting from that to the first atom, well, it was a long, complicated process.
Right, and the article mentions that we can't even quite picture the very, very beginning, something about T equals 0 in the Planck time. What's the problem there?
Our current understanding of the universe, like our best model, it works really well up to a tiny fraction of a second after the Big Bang. But if we try to go all the way back to T0, we hit a wall. It's called a singularity, a point of infinite density and temperature, and our physics just breaks down there. We can only go back as far as 1 Planck time, which is about 10 to the power of negative 43 seconds after the Big Bang. Before that, the universe was so extreme, we need new physics to understand it, something that combines gravity and quantum mechanics, which we don't have yet.
So before that tiny fraction of a second, it's basically a mystery, a big unknown. But the article talks about the Planck epoch itself and this idea that all the forces in the universe were unified during that time.
Right. During that super short Planck epoch, from the very beginning up to about 10 to the negative 43 seconds, it's thought that all four fundamental forces, gravity, electromagnetism, the weak force, and the strong force, were all combined into one superforce. The universe was so hot and dense, these forces were all essentially the same.
Then comes inflation, this period of crazy fast expansion, like faster than light even.
Yeah. After the Planck epoch, from about 10 to the negative 36 to 10 to the negative 33 seconds after the Big Bang, the universe went through this insane growth spurt called cosmic inflation. And yeah, during that tiny sliver of time, it expanded way faster than the speed of light. But it's important to remember, it wasn't stuff moving faster than light through space. It was space itself expanding, which is allowed by Einstein's theory of relativity.
Right, that's a key distinction. Okay, so we've got inflation, and then our standard model of cosmology starts to work pretty well around 10 to the negative 12 seconds. What happens between then and the formation of the first atoms?
Okay, so after inflation, the universe is still hot and dense, but it's cooling down and expanding. We get to the quark epoch, around 10 to the negative 11 seconds after the Big Bang. That's when the electromagnetic and weak forces become distinct, and the Higgs field pops up, giving particles mass. So the building blocks for atoms, quarks, and electrons are there, but it's way too hot for them to combine. Think of it like having all the Lego pieces, but they can't snap together because they're shaking too much.
So all the ingredients are there, they're just not coming together yet. What happens next as things cool down more?
As the universe cools, we enter the hadron epoch, around 10 to the negative 5 seconds after the Big Bang. The quark soup cools down enough for quarks to finally bind together, thanks to the strong force, and form hadrons, things like protons and neutrons. Now it's 1,000,000,000 degrees Kelvin, still crazy hot, but at least we've got the pieces for atomic nuclei. Then, around 1 second after the Big Bang, we have the lepton epoch. Most matter and antimatter particles annihilate each other, leaving a little bit of regular matter behind. And that leftover matter, protons, neutrons, electrons, is what will eventually form all the atoms. But why there's more matter than antimatter, that's a whole other mystery.
So now we have protons and neutrons, the building blocks of atomic nuclei. When did those actually start to form?
That's Big Bang nucleosynthesis, which happens a few minutes after the Big Bang. Protons and neutrons start fusing together, forming the nuclei of the lightest elements. Mostly hydrogen, just single protons, and helium-4, which has 2 protons and 2 neutrons. There are tiny bits of other stuff like deuterium and helium-3, but those are much rarer. But remember, at this point, it's just nuclei, no electrons attached yet. It's all still a hot, ionized plasma.
Right, so the universe is this hot, opaque soup of charged particles. What changes that?
That's the photon epoch, which
Yeah.
lasts for about 380,000 years. The universe is like a thick fog because light can't travel very far without bumping into all these charged particles. Finally, around 3,000 Kelvin, the electrons are slow enough to be captured by those nuclei, forming neutral atoms. That's recombination. And it's a big deal because it makes the universe transparent.
That's when the universe first became transparent, right? That's when the cosmic microwave background radiation was released, that first light from the early universe that we can still see today. Wow, what a journey from that unimaginable beginning to the first atoms.
Yeah, it's mind-blowing to think about the sheer scale of time and energy involved. And the whole process from the Big Bang to atoms, It highlights how complex even the simplest things really are.
All right, let's shift gears again and talk about something that seems simple but is actually pretty weird when you think about it.
Hmm.
Do atoms ever really touch each other? Like when I put my hand on a table, what's going on at the atomic level?
That's a great question. We think of touching as straightforward, right?
Hmm.
But at the atomic level, it's way more complicated. Atoms don't really have hard surfaces like we imagine. They're more like fuzzy clouds of probability, constantly moving and interacting with each other.
Yeah, the article talked about the nucleus being tiny and electrons existing in these probability clouds that could technically extend forever, even though they're most likely to be found close to the nucleus. So it's not like two billiard balls clinking together.
Exactly. Quantum mechanics tells us we can't pinpoint exactly where an electron is, only the probability of finding it in a certain region.
Mhm.
And those probability clouds don't have sharp edges, they just fade out. So in a quantum sense, there's not really a defined surface for an atom to touch.
Okay, so if atoms aren't really touching in a solid way, what's happening when I push on a wall and feel that solidity?
What you feel as solidity is actually the electromagnetic force at work. As atoms get close, their electron clouds start to overlap. And because of the Pauli exclusion principle, which is a fundamental rule in quantum mechanics, no two electrons can be in the exact same state. So as the clouds get closer, the electrons have to shift to higher energy states to avoid being in the same state. And that takes energy, which is why you feel resistance, the solidity.
So it's the repulsion between electron clouds that makes things feel solid. And the article also mentions van der Waals forces, which are like a weak attraction between atoms. How do those play into touching?
Van der Waals forces are another example of the electromagnetic force, but it's a more subtle effect. They come from temporary fluctuations in the electron clouds, creating these tiny fleeting dipoles that attract each other. They're weaker than the forces that hold atoms together in molecules, but they're still important, like for how geckos stick to walls. So it's not really touching in the usual sense, but it is atoms getting close enough to feel each other's electromagnetic fields.
What about the nuclei, the tiny centers of atoms? Could they ever touch?
Nuclei touching is very rare because they're all positively charged, so they repel each other strongly. But there's this quantum thing called tunneling, where particles can sometimes pass through barriers, even if they don't have enough energy to do so classically. This is how nuclear fusion happens, where two nuclei get close enough to overcome the repulsion and fuse together, releasing a lot of energy, like in stars. So, in a way, you could say that's a form of nuclear touching, but it's not something that happens easily.
So touching at the atomic level, it's not what we think. It's a dance of electromagnetic forces, quantum mechanics, and it's what gives us the world we experience.
Absolutely. And understanding those forces and rules at the atomic level, it explains so much about the world around us.
Okay, here's another question that seems basic, but is actually pretty interesting. Are two atoms of the same element really identical? Like, is a carbon atom just a carbon atom no matter what?
Not necessarily. Even if they have the same number of protons, which defines the element, there are still ways they can be different. Their electrons can be in different energy states, for example. Think of a neon sign. The light comes from electrons in excited states falling back to lower energy levels. But not all neon atoms in the sign are excited at the same time, so they're not identical in that sense.
So even if they have the same number of protons and electrons, their energy states can be different. What else?
Even if they have the same electron configuration, they might be moving at different speeds. Like in a solid, the atoms are kind of vibrating in place, while in a gas, they're zipping around much faster. So their motion can be different, even if they're the same element.
Okay, so energy states and motion can make them different, but what if they're both at rest and have the same electron configuration? Are they identical then? The article mentioned isotopes, so maybe that's relevant.
Isotopes are definitely important. Even if two atoms have the same number of protons and electrons, they can have different numbers of neutrons in the nucleus, which makes them isotopes of the same element. And while isotopes have similar chemical properties, their masses are different, and they can behave very differently in nuclear reactions. Carbon-14 dating, for example, relies on the fact that carbon-14 is radioactive, while carbon-12 is stable.
So same element, same electron configuration, same motion, but different isotopes, still not truly identical. Anything else?
Believe it or not, there's even more. Just like electrons, protons, and neutrons in the nucleus can also be in different excited states. And the nucleus itself can have different properties like spin. So even if you had two atoms with the same number of protons and neutrons and the same electron configuration, their nuclei could still be slightly different.
So it's really, really hard to find two atoms that are exactly the same in every way. The article even said that proving two atoms are identical, like down to the quantum level, could win you a Nobel Prize.
Yeah. Quantum mechanics says that if two atoms have all the same properties, they're indistinguishable. But in reality, there are so many possible states for an atom that it's almost impossible to find two that are perfectly identical in practice.
Okay, let's move on to something a bit more visual. Does an atom have a color? Like, if everything is made of atoms, do those atoms themselves have colors?
That's a great question. We see colors everywhere, and it's natural to think those colors might come from the atoms themselves. But color, as we see it, is actually a creation of our brains, not an inherent property of atoms. It's all about how our eyes detect and interpret different wavelengths of light.
Right, color is about how we perceive light. So to understand atomic color, we need to understand light itself, right?
Exactly. Light is a form of electromagnetic radiation that travels in these tiny packets of energy called photons, which also act like waves. The electromagnetic spectrum is huge, from radio waves to gamma rays, but our eyes can only see a tiny part of it, the visible light spectrum. That's why we see colors, because different wavelengths of visible light correspond to different colors. The article even mentioned that our eyes probably evolved to see these wavelengths because that's the part of the spectrum that travels well through water, where life first began.
That's fascinating. So how does light interact with atoms to create the colors we see in objects, like a blue shirt?
When light hits an object, the atoms in that object can absorb some of the light's energy. That absorbed energy can bump electrons in the atoms up to higher energy levels. They can also re-emit light, either at the same wavelength or a different one. The color we see is the light that's reflected back to our eyes. So a blue shirt looks blue because it absorbs most colors except blue, which it reflects. And the way light interacts with an object also depends on the arrangement of the atoms, which is why snow and ice look different, even though they're both water.
So for big objects, color comes from the collective behavior of a ton of atoms interacting with light. But what about a single atom? Can it reflect light and have a color on its own?
That's where it gets tricky. Atoms are much, much smaller than the wavelengths of visible light. So a single atom can't really reflect light in the way a big object does. It's like trying to reflect a huge ocean wave off a tiny grain of sand. It just doesn't work that way.
Okay, so no reflection. But what about other ways atoms emit light, like thermal radiation or the light from a neon sign? Can that be considered an atom's color?
Well, with thermal radiation, like the glow from a hot object, the light emitted is a continuous spectrum, meaning it have all the colors. The overall color depends on the object's temperature, not the specific atoms. But with gas discharges, like in a neon sign, you do get specific colors. The electric current excites the atoms, and as their electrons jump between energy levels, they emit light at very specific wavelengths, which correspond to specific colors. Each element has its own unique set of these emission lines, kind of like a fingerprint. So in a way, you could say that's the atom's color, but only when it's excited by something like electricity.
So while a single atom can't really reflect a color, each element does have a unique way of emitting light, a specific set of wavelengths that act like a color fingerprint.
Yeah, that's a good way to put it. It's a different kind of color than what we see in everyday objects, but it's still a way that atoms interact with light and emit specific colors.
All right, let's dive into the nucleus, the heart of the atom. We know it's packed with protons, all positively charged, and those charges should repel each other. So why doesn't the nucleus just fly apart?
You're right, the repulsion between those protons is strong, incredibly strong at those tiny distances. But the nucleus is held together by another force, even stronger than the electromagnetic force, the strong nuclear force.
The strong nuclear force, that must be pretty intense to overcome all that repulsion.
It is. At the super short distances within the nucleus, it's about 100 times stronger than the electromagnetic force.
Yeah.
But it's also very short range. It basically only works inside the nucleus. Understanding this force is where things get really complicated, and that's where quantum chromodynamics, or QCD, comes in.
Quantum chromodynamics, that sounds heavy. What does it tell us about the strong force?
Well, QCD tells us that protons and neutrons aren't actually the most fundamental particles. They're made up of even smaller particles called quarks, which are held together by other particles called gluons. And gluons carry this thing called color charge, which is kind of like electric charge but totally different. And the strong force is all about how these color charges interact through the gluons. There's also this thing called color confinement, which means that you can't have a free quark or gluon by itself. They're always bound together in groups, like the three quarks that make up a proton or neutron.
So gluons are like the glue holding the quarks together inside protons and neutrons. But how does that explain the attraction between protons and neutrons in the nucleus?
The force between quarks is the strongest, but there's a residual effect that acts between the protons and neutrons themselves. It's mediated by particles called mesons. And even though this residual strong force is weaker than the force between quarks, it's still stronger than the electromagnetic repulsion between protons at those very short distances. Think of it like this. The strong force is like super strong glue that works only up close, and it's strong enough to hold the nucleus together, despite the electrical repulsion trying to push it apart.
So it's a tug of war between these forces, and thankfully the strong force wins, otherwise atoms wouldn't exist.
Exactly. And it's this delicate balance that gives us the diversity of elements we see in the universe.
This next question is a big one. How big is a proton? I mean, they're the building blocks of atoms, but how small are they really?
Yeah, figuring out the size of a proton is actually a lot harder than you might think. You can't just put it under a microscope.
Mm.
Protons aren't solid balls. They're more like fuzzy clouds of quarks and gluons. And the way we measure their size is by looking at how other particles like electrons scatter off them.
So it's like trying to figure out the shape of something by throwing things at it and seeing how they bounce off.
Pretty much. For a long time, everyone agreed that a proton was about 0.8768 femtometers across, which is incredibly tiny. A femtometer is 1/4,000,000th of a meter. But then, in 2010, an experiment using muons instead of electrons found a smaller value. Muons are much heavier than electrons, so they get closer to the proton and give a more precise measurement. And this discrepancy, well, it caused a big stir in the physics world. Some people thought it meant there was new physics we didn't understand.
So a tiny difference in measurement created this huge mystery.
It did. But then more recent experiments, both with muons and electrons, have confirmed that smaller value. It turns out it was probably just a really, really difficult measurement to get right. So as of now, we think the proton is about 0.833 femtometers across, which is still mind-bogglingly small. But the whole saga highlights how challenging it is to measure these fundamental properties of the universe.
Okay, here's another one that seems counterintuitive. If atoms are mostly empty space, how can things feel solid? I mean, if I'm mostly empty space and this table is mostly empty space, why don't I just fall right through it?
It's a great question, and it gets to the heart of how we perceive the world. Imagine if we could magically scale up a table so its atoms were the size of melons. The table would be gigantic, right? But even at that scale, most of it would still be empty space. The nuclei would be tiny specks inside those melon-sized atoms, and the electrons, well, they wouldn't be orbiting like planets. They'd be more like swarms of bees buzzing around those nuclei, too fast to see individually.
Okay, so even blown up, it's still mostly empty space. But why does it feel solid?
It all comes back to those electrons and the Pauli exclusion principle. Those swarms of electrons are all doing their own dance, following specific patterns dictated by quantum mechanics. And the exclusion principle says that no two electrons in an atom can have the same dance moves. So when you push on the table, the electrons in your hand get close to the electrons in the table, and they can't just pass through each other because of the exclusion principle. They'd have to change their dance moves, which requires energy. And that energy is what you feel as resistance, the solidity of the table.
So it's not the empty space that matters, it's the way those electrons interact that creates the feeling of solidity.
Exactly. It's the quantum rules governing those tiny particles that give rise to the macroscopic properties we experience every day.
Okay, next question. Why do atoms even bother forming molecules? Like, why don't they just stay as individual atoms?
That's a great question. It's all about energy, as the article likely explained. Atoms, like everything else in the universe, tend to seek out the lowest energy state, the most stable configuration. Think of a ball rolling down a hill. It'll naturally settle at the bottom where its potential energy is lowest. Atoms are kind of the same way.
So how does forming molecules lower their energy?
We'll take the simplest molecule, hydrogen gas, H2. When two hydrogen atoms are far apart, their total energy is basically the sum of their individual energies. But as they get closer, their electron clouds start to overlap, and the electrons can interact with both nuclei. This creates a new shared energy state that's lower than the energy of the two separate atoms. That's a covalent bond, where the atoms share electrons to achieve a lower energy state.
So it's like teamwork, sharing electrons to be more stable.
Exactly. And the article likely explained how the exact distance between the atoms in a molecule is determined by the balance between attractive and repulsive forces. If they're too close, the nuclei repel each other. If they're too far apart, the attraction from the shared electrons weakens. There's a sweet spot where the total energy is minimized, and that's the bond length.
And what about more complex molecules, like water?
For more complex molecules, things get more complicated, of course, but the basic principle is the same. Atoms bond together to achieve a lower energy state. And the specific ways they bond are governed by the same quantum mechanical rules that determine the behavior of electrons. For example, the article likely talked about how atoms try to fill their outermost electron shells, which makes them more stable, like the noble gases. And this desire to have a full outer shell is what drives much of chemistry.
So it's like atoms are playing a game of electron musical chairs, trying to grab a seat in a full shell by forming bonds with each other.
It's a good analogy. And the rules of the game are set by quantum mechanics.
Okay, this next question is about something truly extreme. Neutron stars. Are they basically just giant atoms?
That's an interesting way to think about it, and the article probably explored the similarities and differences. Neutron stars are some of the most extreme objects in the universe. They're born when massive stars die in these incredibly violent explosions called supernovae.
I remember reading that they're incredibly dense, like a teaspoonful would weigh billions of tons.
That's right. They're only about 10 to 20 kilometers across, but they pack more mass than our sun into that tiny space. And their gravity is so strong that atoms are crushed, forcing electrons and protons to combine into neutrons. That's why they're called neutron stars. They're essentially a giant ball of neutrons.
So how is that similar to an atom?
Well, in an atom, you have the nucleus, which is held together by the strong force, right? And in a neutron star, you have this giant ball of neutrons, also held together by the strong force, but it's gravity that's providing the pressure to overcome the neutrons' tendency to repel each other. So in a way, you could say that a neutron star is like a giant nucleus, but instead of being held together by the strong force directly, it's gravity that's driving the interaction.
So similar in the sense that the strong force is involved, but different in scale and in the role of gravity.
Exactly. And there's a lot we still don't know about neutron stars, like what exactly happens in their cores. Some scientists think they might be made of even more exotic stuff, like a quark-gluon plasma, which is what the universe was like in the first fraction of a second after the Big Bang.
Wow, that's wild. So neutron stars are like a glimpse into the extreme conditions that existed in the very early universe. Okay, this next question is truly mind-boggling. What if the entire universe is just an atom?
That's a really fun thought experiment, and it highlights how much we still don't know about the true nature of reality. It plays on the idea of scales, like how atoms are tiny compared to us, and we're tiny compared to planets, and planets are tiny compared to stars, and so on. So could the whole universe be just a tiny part of something even bigger? It's a very old idea, going back to ancient philosophers.
The article mentions a few theories, like the one-electron universe and the multiverse theory.
Yeah, those are some interesting takes on this question. The one-electron universe is this wild idea that there's only one electron in the whole universe, and it's zipping back and forth through time, creating the illusion of all the electrons we see.
That's wild. And what about the multiverse?
The multiverse idea suggests that there might be many, maybe even an infinite number of universes, all existing alongside each other. And maybe our universe is just one tiny bubble in this grand cosmic foam. And in some versions of the multiverse, each universe could be like an atom in a larger structure.
So it's like a never-ending nesting doll of universes.
Exactly. But it's important to remember that these are just theories, ideas that people have explored. There's no scientific evidence to support them yet, although there are some physicists trying to find evidence for the multiverse.
It's definitely fun to think about, though.
Absolutely. And these questions about the ultimate nature of reality, they push us to think beyond our current understanding and to imagine possibilities that might seem crazy at first.
All right, let's get a bit more personal now. What happens to our atoms after we die? Do they just disappear?
Not at all. One of the fundamental laws of physics is the conservation of matter. It basically says that matter can't be created or destroyed, only transformed. So the atoms that make up your body, they've been around for billions of years, cycling through the universe, and they'll continue to exist long after you're gone.
So where do they go?
Everywhere. They become part of the environment, they're taken up by plants and animals. They might even end up in space. Think about it. The water in your body, that's mostly hydrogen and oxygen, right? When you die, that water will eventually evaporate, become part of the atmosphere, maybe fall as rain, be taken up by a plant, and eventually end up in someone else's glass of water. Or it could be split apart by sunlight, and its hydrogen could escape into space, eventually becoming part of a star-forming nebula.
That's pretty amazing to think that our atoms can be part of this vast cosmic cycle.
It is. And it's not just water, it's everything that makes up your body. The carbon, nitrogen, phosphorus, calcium, all of it gets recycled and reused in countless ways.
So even though we die, our atoms live on, becoming part of the world around us and beyond.
Exactly. In a way, we become one with the universe, our atoms dispersed across space and time.
Okay, last question, and it's a big one. Do atoms last forever?
That's a question that has puzzled philosophers and scientists for centuries. On the one hand, we know that matter is conserved, so atoms don't just disappear. But on the other hand, we see things changing and decaying all the time. So is anything truly eternal?
The article talked about radioactive decay, where unstable atoms break down over time.
Right. Some atoms, particularly heavier ones, are inherently unstable because they have too many or too few neutrons in their nuclei. And over time, they undergo radioactive decay, emitting particles and energy until they reach a more stable configuration.
So some atoms are definitely not forever.
True. And there's even a theory that protons, those seemingly stable particles in the nucleus, might actually decay over incredibly long timescales, like billions of times the current age of the universe. If that's true, then even the most basic,